Okay, so for R superscript j, where the cardinality of j is greater than or equal to aleph null, that is, it is infinite, the uniform topology is strictly finer than the product topology, since the arbitrary open ball in the uniform metric is a product of uniform intervals about each coordinate is not open in the product topology, and this is since it is not true that all but finitely many of the open sets in the product are the entire real line, or is the entire real line. Also, the box topology is strictly finer than the uniform topology, since an arbitrary product of open sets that does not contain a product of uniform intervals is not open in the uniform topology. Now, for finite dimensional real space, the three topologies coincide. Another thing to notice at this point is that for R sub j, where the set j is uncountable, the space Rj is metrizable only in the uniform topology. While R omega, a countable product of real spaces, is metrizable in both the product and uniform topologies. And finally, finite dimensional real space is metrizable in all three topologies. And in fact, all three topologies are the same in finite dimensional real space. All right, so we will end this lecture by beginning to look at continuity in metric spaces, and we'll continue that study in the next lecture along with sequences and limits in metric spaces. So let x together with a metric d and y together with a metric rho be metric spaces. And let f be a function from x into y. Then the function f is continuous if and only if for every point x in the set x and for every epsilon greater than 0, there exists a delta greater than 0 such that the distance between x and y is less than delta, implies that the distance in the metric rho between f of x and f of y is less than epsilon. So again, a function f is continuous if and only if for every point x in the space x and for every choice of the radius epsilon, there exists a delta greater than 0 such that if the distance between x and y is less than delta, then the distance between f of x and f of y is less than epsilon in the metric rho. Now, another way to state this is that there exists a delta neighborhood about x such that the direct image of this neighborhood is contained in an epsilon neighborhood of f of x. And we'll use this equivalent statement in the proof. So suppose that the function f is continuous. Then, for every point x in the space x, and for every choice of epsilon, the inverse image of the open ball in the metric rho centered at f of x with radius epsilon is an open set in the space x that contains the point x. So we have an open set containing a point in the space x. So there exists an open ball in the metric d centered at x with radius delta such that the point x is in this open ball, which is a subset of the inverse image of the open ball in the metric rho centered at f of x with radius epsilon. So let the point y be in this open ball. Then the distance in the metric d between x and y is less than delta. Further, f of y is in the direct image of the open balls centered at x with radius delta, which is a subset of the direct image of the inverse image of the open ball in the metric rho centered at f of x with radius epsilon. Now, since the direct image of an inverse image of a set is a subset of the given set. We have that f of y is in the open ball in the metric row centered at f of x with radius epsilon. And so the distance in the metric row between f of x and f of y is less than epsilon. All right, so conversely, suppose that the epsilon delta condition holds, and let the set V be open in the space Y. We need to show that the inverse image of the set V is open in the space X. So let the point X be in the inverse image of the set V. Then the direct image of X, or f of X, is in the direct image of the inverse image, correction, is in the direct image of the inverse image of V, which is a subset of the set V. Now V is an open set in the space Y, and so there exists an open ball in the metric row centered at f of x with some radius epsilon, such that the point f of x is in this open ball, which is a subset of the set V. Now, by the epsilon delta condition, there exists a neighborhood or an open ball in the metric D centered at x with radius delta, such that the direct image of this open ball is a subset of the open ball in the radius, or rather in the metric row centered at f of x with radius epsilon. And so we have that f of x is in the direct image of the open ball centered at x with radius delta, which is a subset of the set V. And so the point x is in the inverse image of the direct image of the open ball in the metric D centered at x with radius delta, which is a subset of the inverse image of the set V. Now, since the inverse image of a direct image contains the set of a set contains that set, we have that the open ball in the metric D centered at x with radius delta is a subset of the inverse image of the direct image of that set. And so we have that the point x is in the open ball in the metric D centered at x with radius delta, which is a subset of the inverse image of the set V. So what we have demonstrated for every point x in the inverse image of the set V, there exists an open ball in the metric D centered at x with radius delta, such that the point x is in this open ball, which is a subset of the inverse image of V. And so the inverse image of V is open in the space X. All right? So we'll look at a very quick example. Let F be a map from the real line into the real line. Then the function f is continuous if and only if for every point x in the real line there and for every choice of epsilon there exists a positive delta such that if the absolute value of the difference between x and y is less than delta, then the absolute value of the difference of f of x and f of y is less than epsilon. Now another way to state this again is that f is continuous if and only if for every point x in the space R, or in the real line R, and for every choice of epsilon, there exists a delta neighborhood of the point x such that the direct image of that neighborhood is a subset of the neighborhood of f of x with radius epsilon. So in the real line, the metric D is going to be the standard metric. And so we have an open ball in the standard metric, so that is the direct image of an interval about x. And this must be contained in an interval, an epsilon interval about f of x. All right, so we'll end here for today. Next time, as I stated, we will continue studying continuity, and we'll look at sequences and limits in metric spaces, and look at the concept of a complete metric space. So I hope you have enjoyed the 18th lecture. Thanks for watching.